Hey, is everybody ready for some mad science? Yeah, that did not impress me at all. Is everybody ready for some mad science? Everybody welcome our mad scientist, awesome Alyssa.
How are you doing today, everybody? Good. Nice, nice. Good to see you all. I am your mad scientist, awesome Alyssa, and I am here to present our Wacky Winter Show. Now, when I say I'm a mad scientist, that doesn't mean I'm crazy or doing weird things like making monsters in my basement. It just means I'm crazy passionate about science, and I'm here to share that passion with you guys. Now, before we get into all the cool science stuff, I do have a few rules that we need to go over. This just to make sure that we're having safe science fun, okay? So, my first rule is, do you see all of this stuff on the table? I'm going to ask you not to touch it unless I say that you can. Turns out I am a real scientist, so I am dealing with real chemicals and some really fragile or breakable equipment, and I just want to make sure that it's safe for you all before passing it off, all right? So I like to say rule number 1 is no touchy my stuffy, got it? Yeah, that's an easy one. All right, this one might be a little bit difficult because it's the weekend and we're having a relaxing Saturday, but we do ask that if you have a question that needs an answer, or an answer to any of my questions, or anything else you think my show may need, just ask that you raise your hand. Raising your hand gives everybody a chance to share their opinions without being interrupted, and that's important because science is peer-reviewed. That means we work together to get to the answer sometimes, alrighty? So let's do a quick test run since it is a holiday weekend. So we are going to raise our right hand. Sorry, I'm not here, friends. All right, good job. Sometimes I trick them, sometimes I don't. And then we're going to raise our left hand. Good job, guys. Good job. Put that one down. And then we're going to raise both hands. That was an easy one. We can shake that out for 5, 4, 3, 2, and all right. So you guys didn't forget how to raise your hands over the weekend. Good to see. All right. And then my final rule, which is my personal favorite, is that we have fun. And just so I know that that rule is locked into your brain really, really tight, I need you to repeat the words have fun on the count of 3. 1, 2, 3. Alrighty, let's have some fun. And let's start our science fun by getting our brains thinking like a scientist. And what better way to do so than with a question? So I have a question for my friends in the audience. I know, apologies my friends. I am still testing out this stage. So my question is, can anybody tell me the difference between a scientist and a magician? And there is a challenge, you can't use science or magic in your answer. Yeah. Scientists aren't making things up. We're usually doing experiments and testing things to see what the truth is, whereas, I don't think a magician's doing the work to explain what's going on. They're hiding the truth. I like that observation. Does anybody else have an answer for the question? Yeah. Magicians aren't going to share what they find either, right? They're going to do all these awesome things that confuse your brain, and they're never going to tell you how it works. Whereas as scientists, we may do some brain confusing things, but our job is to figure out and explain to everyone to make sure that we all understand how it works. And I'll take one more answer to my question. My friend right here in the green. Exactly. So our friend said magicians are doing magic, they're doing tricks and illusions, and as scientists we're discovering things. Like for example, paleontologists discovered dinosaur bones and other ancient things. So these are great observations, right? The most important of the two, or the ones we like to point out, is that sometimes magicians are doing science, but they're never going to explain it to you, okay? Their bread and butter is keeping that science, those tricks, a secret. All right? Whereas, like I said, a scientist everyone. Now, I am a scientist, but I did pick up a magic trick along the way. Would we like to see that before we get started? Alrighty. I do need one volunteer to help with my magic trick, though. It is a card trick. My friend right here, come on down. Alright. What is your name? Jamo? Nice. Alright. So, Jamo, I usually have my friend pick a card, but I haven't shuffled my cards today. So before we pick the card, we're going to do what we call a mad science shuffle. So I want you to go a little bit into the deck, about maybe this far, and you're going to take this stack here, flip it over, yep, and then put that back down on top. All right? Now, one shuffle is not enough in my opinion, so we're going to do it one more time. But we want to go further than the cards that we can already see, so maybe this one. Yeah, pick them all up. Flip them over, put them back down, all right? And I usually give my friends the cards on the top, but I can see what's on the card on top, so I'm gonna take them away. Put them back. That leaves us with this one, Jamo. So I want you to look at the card, memorize it, don't show it to me, and then show it to our friends in the audience. Once everybody in the audience has it locked into their brain, show me with the thumbs in the air. Don't forget our friends over there, okay? Alright, so now I'm going to take this card and do my very best to make it disappear. Do you think I could do it? Oh, I hear some mixed, answers. I'm not shocked. Alright, are we ready? 1, 2, 3. Ta-da! It's gone? Where? My pocket, guys, there's nothing in that pocket. The other pocket's still empty. Yeah, the other pocket, right? Because I'm not a magician, I can't make things disappear. So that was my silly attempt. Now the best I can do as a scientist is change it. So would we like to see the card be changed? All right, you're gonna help me. I need you to just take the card and rip it in half. Perfect. Now I'm gonna take that back. And my friends in the audience, is this the same thing we started with? What do you think, Jamo? No, it doesn't look like the same thing because it's split into 2 pieces. But it still feels the same, and I can kind of put it back together to make it look the same. So all we really did was break it into parts. So at the end of the day, it's still a card. When you make a change to something, but it's still the same thing, and you can tell it's the same, that's a physical change, right? So we physically changed this card. But I do think that's a little dull, and I like fun and excitement as a mad scientist. So would we like to see an exciting chemical change instead? Yeah, all right, so to get this chemical change started, I need you to rip this up a little bit more, get them smaller pieces, put those pieces in the pan, all right? While you're doing that, I'm going to explain the chemical change or the reaction we are going to see. We are going to see a fire, okay? It's okay, I am a trained professional, but I do want to go over what we need to make a fire, all right? What Jamo is carrying up, our card, is usually our kindling, something to burn. Sometimes if you have a fireplace at home, that would be your firewood, or in the grill, charcoal, just something for that fire to consume while it's eating, all right? Also, to continue to get that flame a little brighter, I'm gonna add fuel. Today's fuel is isopropyl alcohol. You might recognize that chemical from your first aid kit. It's really good for cleaning out cuts and wounds. But scientists like it too because it's combustible, meaning it's able to catch flame as well. So that will help our fire grow a little bit. And then once that blaze is growing, it is going to eat oxygen, consume the air around it. So 3 things that we usually use to make a fire is kindling, fuel, and oxygen. All right, how's our fire coming along? We got small pieces? Perfect. Now, because I am bringing out some chemicals, I'm going to let you borrow my eyeballs because I'll be further away. All right? And I'm just going to add a little bit, not too much. Just a little bit of fuel. We don't want our fire to be too big. Nothing too crazy, just a little. And then I'm going to grab my lighter. Put fuel out of the way and start a brief fire. There we go. It's growing. Oh, wow, it's really growing. It started growing a lot faster than I thought I would. I think I was a little heavy-handed with our fuel. No worries. I've covered the fire with a lid. Do we think the lid was able to put out the fire? Ooh, mixed answers from our audience. What do you think, Jamo? Do you think we put out the fire? No? All right. Understandable. So since you guys don't believe it, the fire's out, I'll look, and if it's safe, I'll pass it along to you to share. All right. Can I get a countdown from 3? 3, 2, 1. Oh, there's no fire. What's that? Want to take it out, Mr. Work Friend? Is that your car? All right. Can we give a round of applause for Jamo? Thank you so much. You're so brave with our fire. Now, I did mention that that was my secret mad scientist magic trick I've learned over the years, but I am willing to take some guesses or some hypotheses onto how you think my magic tricks work. Yes. That's not a bad guess. Our friend says she thinks maybe the card was already hidden beforehand. So it was already inside and that the card we ripped up was a fake deploy. Yeah, good guess. And then you as well. Oh, that's a good guess too, because we said chemical changes you usually end with something different. So maybe the fire was able to change it back to what we thought we couldn't put it back together before. That's not a bad guess either. And I thought I saw one more hypothesis. Yes. Oh, you too, I got you. So there were 2 cards before, so one was on hand and we ripped up the other one. So I like this idea of a trick card. And then last but not least, I saw your hand too. So another fire fusion guess. These are great hypotheses. But like I said, it is a magic trick, so I will not tell you which one is the correct answer. All right? No worries, we will continue along with our show. I think we should bring along our friend Egbert, because he's going to help us understand some things. All righty? Oh, you know what? Actually, I'm sorry, Egbert. I do want you. I'm a big fan of Egbert, but I think we should look at something else. Because we talked about what we need to make a fire, right? Kindling, fuel, and oxygen. So let's talk about what's usually left over. Alrighty? So I have a piece of paper, and I am going to quickly set it on fire. And I want you to observe what's left behind, okay? What do we see when I start a small fire? So do we see a little bit of orange, that ember glow, the light? It's also getting a little warm up here, so we also feel heat. Alrighty, or fire can be considered a product of heat. And then what's falling from the paper when I tap it? Ashes. And then what's floating up in the air? Smoke. Good eyes, guys. So, as scientists like to say, we usually get light, heat, smoke, and ash from fire. Can we say that together? Light, heat, smoke, and ash. One more time, friends. Light, heat, smoke, and ash. So that's usually what's left over when we burn something like paper or wood, and that's because the sugars in there change to those products. But we're scientists, and we usually like to test the boundaries of nature. So we kind of created a different kind of paper. Now, it's still made out of plants and trees like our regular paper, but we also added a gas, okay? Did you have a question, my friend? Oh, so maybe when I do the paper in a pan and spin it, we could get a little tornado? That sounds really cool. Though it does sound hazardous because aren't tornadoes wild and sometimes uncontainable? And we don't want to accidentally, this is a lovely ballroom, we don't want to accidentally make a fire that's uncontainable. But I like your mind, maybe in a bigger space, all right? So, this paper treated with the gas burns differently. So I'm going to set fire to it, and I want you guys to look closely. We are looking for light, heat, smoke, and ash. And then, is this a question before I light your paper? Plastic is a little different. Plastic will burn and it will start to melt as well as sometimes change color. But because of what it's made out of, and it's a very durable product, it's sometimes hard to melt all the way down to ash without burning it for a really, really long time. That is a great question though. I like how your mind works, all right? So watch closely. We are looking for light, heat, smoke, and alrighty guys. Did you see any lights? And it was a little warm, I felt the heat. But was there any smoke? Or ash? Maybe we missed it. One more time? Let's see. There isn't any smoke or ash. What do we think happened? Are you guessing or did you have a question? Oh, that's a great question. Our friend wants to know, why does it look like it just vanishes into thin air, right? Does anybody have a guess? Yeah. Oh, I like that observation. You notice that with the gas-treated paper, the fire kind of grew more than just going out and turning into ash. So there was something on that paper that allowed that fire to just keep burning without producing any product. Great observation. What is your guess, my friend? Oh. So there was, something in the air that puts it out? All right, that's not bad either. Maybe it interacted with something in the air. And then my friend in the blue coat up front here, what was your hypothesis? Absolutely, that is a great observation. The gas is what made that paper burn differently, okay? Because of the gas the paper is treated with, nitrogen gas, it exists naturally in our atmosphere. And it doesn't, there's extra paper. All right, and it doesn't like to be solid. It'd rather be in its loose gaseous state. So when I add heat or fire, I'm exciting that gas and it gets all hyper and it just goes back into it. That, my friend, is why it looks like it vanishes into thin air, because it's turning back into that air. Now, when something in science goes from a solid back into a gas, we call that sublimation, okay? So that means instead of ice turning into water, if it skips directly into the water vapor, it has sublimated, alrighty? This paper is sublimated. Would we like to see an entire one burn before we move on? Yes, yes, yes. Alrighty. And then it's gone in a flash because those solid particles have dissolved into that nitrogen gas and it's just floating around our atmosphere now. Alrighty. Let's see. Now we can bring my friend Snowman Egbert out. Did you have a question, my friend, in the idea? Oh, how does fire? So, remember I mentioned that fire is a product of heat? So fire occurs when something's really, really excited, okay? So it's basically the next step before it goes into that gas state. It's something technical. Does that make sense? Cool, cool, cool. And then I'll take my friend here. So sometimes the fire has to go away before the rest of the stuff can appear. That's a great observation. But sometimes you won't get smoke products until the flame is gone. I like that you noticed that. And then I saw you here and we'll move on. Oh, because as that fire was blazing and heating up and converting that nitrogen back into the gas, it wasn't leaving anything else behind. So it completed the reaction and changed it all into a different form. Exactly, it changed its state. Great question though, absolutely. Alrighty, so our friend Snowman Edward, he's gonna help us out because we like to take him out. He's our lab assistant and we'll put him in his travel lab, okay? So I'm gonna get him in the travel lab and we'll get started, alright? Good observation, my friend. Snowman Egbert does not fit. I am having a hard time. I don't know if we used too hard of a snowball this year, but he's not getting into his lab. I need some guesses. Can two friends share some ideas on how to get them inside? My friend right here. Yep, in the wicked shirt. How are we going to get him in? It's okay. If it comes back, raise your hand. My friend over here in the orange, is that orange? Yeah. Okay. Squeeze them into a line. Like that. Alright. Oh, I think we did it. Oh. Not a bad hypothesis. Making him smaller. It's not quite working though. And my friend in the tutu back here. In the pink. So maybe a little bit smaller than I tried before. Alright, I'll do it as best as I can. I don't know how small I can get him. You know, mass can't be created nor destroyed. I'm not sure. Okay, alright. I either have really slippery hands or he's just not fit. I'm going to give you guys a hint before I take another guess on how to get him into it, okay? Because although Edward is a little extra plump this year, there's also something in that flask keeping him out. It might look empty, but there's something in there. Does anybody have a guess? My friend way in the back here. Orange zipper? Yep. Yeah, hydrogen, even some oxygen, even some carbon. There's some gas in that flask that is keeping Egbert out, okay? So, because there's always gas and air in the atmosphere, and if you want to know how much, you can make a small circle with one hand and put it flat against the other. When you do this, you make about 1 square inch, and in that square inch alone, there are 15 pounds of air at all times. So there are always 15 pounds of air per square inch of pressure weighing us down. The rough math is about 2 elephants per person on our shoulders. I know, terrifying, but no worries. We don't get crushed under it because we have the same pressure inside. Same for the glass. It's not exploding under the weight of our atmosphere because there's enough air inside to keep it out. But it's also keeping Egbert out. So we need to get rid of the air to get Egbert in. How am I going to do that? Do you have a guess? They actually do float. So gas is the state of matter that's always moving. So they're going to take up the space that they're able to take up. So they're stuck inside the flask. But when I take them out, they're moving at that equal pace to make that balance inside and outside. Alrighty? But does anybody know how I'd be able to get the air out when I seal it? Yeah, my friend in the back. Earmuffs? If you forgot, we can come back if it comes to you. Alrighty, and then right here in the blue, do you know how we'll get Egbert inside? Oh, that's also a great guess, right? Because if this is too small to fit him and we break it, then there's nothing keeping him out anymore. So broken glass is dangerous, and this is a lovely facility. I don't want to leave any hazards behind after my show. Alrighty? I see one more guest over here. Oh, put him in fast. I mean, I don't mind. One more try. Let's see. Like, and then, oh. I don't think I'm coordinated enough. Hold on. Okay. No worries. No worries. You have a guess before I give it up? Oh, maybe we should put something in there that's able to pull him in, right? And we can do that because remember I mentioned that fire eats air too? So maybe if I were to create a fire to consume that air that's keeping Egbert out, it could suck him in, like you guessed? Yeah, should we try it? All right, let's see. So I have the paper. It should catch fire fairly easy. We'll put it in, and then hopefully it should be able to suck Egbert in. Let's see. We don't want his lungs to have a hard time. We can. Okay. So Egbert is stuck in the lab. All right. Good question. How are we getting Egbert out? He just came out with Egbert. All right. Any guesses? I see over here in the burgundy. How do I get Egbert out? Oh, maybe the same thing, a fire? That's not a bad guess. I really don't think it is. The only problem is, Egbert's now in there, and I'm not too sure if he'd ever forgive me for starting a fire in the same place with him. So, maybe I'll take a practice Egbert at home and try it and come back with results for you. Yeah? Yeah? All right, one more guess, right here in the pink snowman. That, right? Because to get Egbert in, I have to take air out. So maybe some air inside would push him back outside again. All right. So you knew that I didn't have a fancy blowing machine. I just have my lungs. So I'm going to first get him feet first so we're not pulling on his noggin. And I'm going to use my strong lungs and try to blow Egbert out. Are we ready? Woo! He made it. Alrighty, good guess, my friend. Did you read the Mad Scientist manual before I got here? Do you have a question? Oh, what was on your way? Oh, yes, that's also not a bad guess, right? Egbert too big to get in and out of the lab. If we just take away his mass form, the size he is, there'd be no problem getting him in and out. Just again, I don't think he'd forgive me for that either. So we're going to keep him intact, alrighty? Now, what did I put on my friend? It's our friend, the snowman Egbert. He may look like a balloon, but he parties with us mad scientists often. Alrighty, so we've talked about fire eating air and stuff like that, but let's talk about particles and how they're combined together, right? So the molecule is repeating over and over again. It is what we call a polymer. And I brought another snowman that is a type of polymer. He is made out of styrofoam. We've heard of styrofoam, correct? Yeah, it's the cup. It's usually makes up our cups that keep our coffee warm, or even some coolers are made out of styrofoam. It's good for insulation. It's also a type of plastic, long-lasting as well, but it's a polymer, meaning it's the same molecule repeating over and over. Did I see a hand raised? Yes. observation, styrofoam balls, they aren't always. It does. Oh, he's not connected all the way. Good eye, good observation. He's just a styrofoam man. Now, those polymers, although they're connected, we're able to take things and separate them. So I brought a chemical that interacts with styrofoam and breaks it down. The chemical looks like my alcohol, but it's acetone, okay? Acetone is found in nail polish remover, and it's good at breaking stuff down. But it's gonna break this polymer, the styrofoam, down into a liquid. So we're gonna make something that doesn't usually melt. Are we ready to witness it? Not the table. Oh, just our snowman. Oh, poor snowman. You know, just like when the sun comes out and melts out all of our snow and snowman, the acetone did the same thing to our friends. Can you see him? Yeah, I don't mind coming to the front and showing you what's left. This is all that's left of our snowman styrofoam. Alrighty, so that acetone changed it from a solid to a liquid. But because it's not the same thing and it's breaking into different kinds of molecules than what we started with, this is a chemical change. Alrighty? Yes. Because this snowman was made 5 minutes ago. That snowman's been in my life for many, many years. It's called attachment. You have a question as well? Because they're not made out of the same thing. Great observation. The wood was able to remain because they're not made out of the same molecules that react with the acetone. You need something a little stronger to melt wood. At least the same way to melt styrofoam. Yes, my friend here. Oh, so the igloo's gonna start melting in the warmth? Yeah. Well, today's a good day though because it's below freezing, so you might get one more day out of it, right? Alrighty. Now, when we're putting on gear, we're usually wearing to protect from the freezing cold. We're usually wearing to knit clothing, right? Such as beanies and gloves and other things to keep our body warm. But does anybody notice that sometimes if they take it off too fast, it makes their hair stand up? Or sometimes after taking them all off and being inside of all that wool for the day, you're going to touch a doorknob and it shocks you? Yeah. Do you recognize that? You want to explain to us what's happening there? How much time do I have? Would you like me to say a quick word for the snowman? Alrighty. Rest in pieces, styrofoam part A and styrofoam part B. My dear styrofoam snowman, your contributions to science and observations were greatly appreciated. Thank you for providing yourself to demonstrate an awesome experience for our friends in the audience. Can we bow our heads and say thank you, Mr. Snowman? Alright, that was very kind. You know, we should usually take a beat for our missing friend. I'll take 3 more questions and I'll move along. 1. Which one? Oh, the alcohol and the acetone. Honestly, by the looks of their chemical makeup, we get a lot of water and hydroxide particles, and maybe some carbon chains. There's a lot of carbon, hydrogen, and oxygen in them, so it would make a lot of the same chemicals over and over. Great question, though. Alrighty. But do we remember talking about the hats and the hats making our hair stand up? Or sometimes when we rub them together, we touch metal and get electrocuted. Do we know what that's called? Static electricity, alright? So a little bit of vocabulary. Static means still. So when we say static electricity, those little particles that make up what turns on our lights. And so when they're not moving and they're kind of just stuck, motionless, still, or static, they build up that negative charge. And they build up on us or our clothes. And when it's built up, it likes to reach out like lightning and ground itself. So that's why sometimes when you touch a doorknob, it'll accidentally shock you. Now I have brought a device that produces static electricity. Alright? So use it. We're going to show you how it works. You might be able to see a little bit of lightning, so we have to look closely, okay? So this is what we call a Van de Graaff machine, and it's going to generate static electricity. The way it does so is with this band inside. It runs around really, really fast, touches something up here, and creates friction. You can create your own friction by rubbing your hands together. Friction sometimes gives off heat energy. You'll feel that between your hands. Or it can also charge up those electrons. Give off static. Build off static energy as well. Yes, my friend. Oh, so you've seen this before? Oh, she's had a preview. Did you have something else? Oh, what do you know it as? Yes, we are not going to play with it. I'm just going to demonstrate the cool things we're able to do. All right? So, it has that band. The band's going to produce some friction, and that's static electricity. And I'm going to get it turned on. This is my discharge wand, so I'll touch it to the bulb anytime to get rid of that electric building. All righty? So, we'll turn it on. See that band starts to move, and as it builds electricity, ooh, you can hear it. See it a bit. Small lightning. You see that one? You can kind of see it. All right, I am going to turn it down. We don't want it running too long. So, as too much buildup of that static electricity, that field can grow and grow and grow. And by the time I go to discharge it with the wand, somebody far, far away, because fun fact, we're also electrical, might discharge it first. So I don't want to accidentally set off on the electrical field that's too big to control. So that is why. So I'll try a couple more lightning to see if a friend over there can see them. I'll try from the top. Already going. Whoa. Whoa. Oh. No worries, no worries. No worries. I'll try one more time for the lightning. And then I know they're small, but I'll show you what that lightning can do when it's not discharged with the wand. Okay? So let's discharge it first, because we don't want to accidentally shock ourselves. We are electrical beings, so sometimes it'll ground to us. Alright? So this styrofoam, kind of similar to the acrylic in our hats and stuff, when we have wool blend, it's going to behave similarly to the floating effect we get with our hair, right? Well, I'm not sure. Do we think that putting the styrofoam will make the lightning visible, or do we think putting the styrofoam will do something else? What do you think will happen? They do look like marshmallows, but they're made out of the same thing that our snowman friend was made out of, and that what's left over doesn't look edible, so those aren't edible either. But let's see what static electricity is able to do to other objects when it's ungrounded for a while. All right? I'm gonna hold my wand, turn this on. It made a little storm. So that's why your hair, other fine particles stand up, because that static electricity charges them and excites them, all right? And that's why if you have frizzy hair standing up after that removal of the hat and you go to touch a doorknob, it's because you built up that electrical field and it just wants to travel somewhere, all righty? Now, my friends, we have come to the favorite part of our wacky winter show, right? Because it's the winter time, so shouldn't we be dealing with some ice a little bit? Just a little bit of ice. So let me grab my mad science ice. What's in there? I like these questions. You're quite the scientist already. I hear some hypotheses as well as to what might be in my cooler. So let's see. Something cold. Ice from the lake. That'd be nice. I wish I thought of that actually. Alrighty. Here is my ice. Alright, so some friends are saying it's dry ice. Do we all agree? Yes, it is dry ice. And you also mentioned that you can tell because we noticed that there's stuff coming off of it, right? And regular ice doesn't usually give off this steam. So we can tell that it's different. Now, do we, oh, but I was gonna ask you, do you know why we call it dry ice? Because it's dry ice. I like that. We'll come back to that. I do see one guess. Do you have a guess? Oh, sorry, my friend. Can I ask my friend in the pink and then come back to you? Absolutely. That's good. That's very safe. And I like that you pointed that out because we talked about ice in our freezer. Dry ice is not the same as the ice in our freezer, okay? The ice in our freezer is made out of water and it freezes at 32 degrees, okay? But this ice is really, really cold. It freezes at negative 190 degrees. So I'm glad that you're not eating this dry ice because I don't think it'd be a very fun time, okay? Yeah, very thick and very cold. That's why I have these gloves on, okay? Oh, I wouldn't doubt it. It's so far away from the sun on that planet. Did you have a question before I continued with my dry ice? Oh, for the Van de Graaff machine? Oh, that's fine. I think I've charged this up enough for the day. I think we'll all be walking out of here with a fair share of static electricity charge. Oh, maybe if I have a little time. That sounds like a plan compromise, if I have time. Alrighty, and then last but not least, I have a couple experiments I need to go through with the dry ice, but I do want to explain to you why it's dry. So like my friend said, it's dry. That's why we call it dry ice. It's not made out of a liquid, so it doesn't melt. As it gets warm, it starts to give off that steam, that heat, see? And as I change it from glove to glove, there's no liquid left behind. So it's dry because it's made out of a gas instead of a liquid. Alrighty? So, because it's made out of gas and not a liquid, it likes to go back directly into that gaseous state. Does anybody remember what it's called when something goes from a solid to a gas and skips the liquid? Here. Close. Something with a C. I think I heard it too. Solid to a gas.
Sublimation.
What's that? I heard it. Sublimation. Yes. Dry ice sublimates. That's the main reason it's dry. You were very close with that sound. Very close. Sublimation. So, I'm just going to add it to water, which is way warmer than the ice, and it'll sublimate or produce that gas faster. Alright? Alright, and now it's coming out in lots and lots of gas. You can, if I plug it, well, it's difficult because this is a beaker, so it'll have that beak to escape. But I like how you think, because I brought another piece of science equipment that I could probably block off. Let's try it in a different type of experiment. So I have a different kind of scientific equipment. It looks like a flask, And it is, but it's special because it has this sidearm. So it gets called a sidearm blaster, okay? All right, so I'm gonna add some water to this. All right, got some water in there. And I'm gonna add some small pieces so we can get that sublimation going. All right. So I like using this to look at what will happen to the gas as it spreads out. Because remember, gas likes to spread out, take up space. It doesn't like to be confined. So this is a good way to observe what happens when you trash. It's like a volcano, but I'm gonna block that off because I want to get it to move a different way, right? So it does have another exit, and my friend's saying, but it's not completely blocked off. So I am willing to try to block it off. But do you think I will be able to contain the gas forever, blocking off all of its exits? So I hear some it's going to explode. Do we think that's the truth? Alrighty, so we will see. Alright, let's get stuff out of the way in case it does go flying. Put my glasses on too in case we do have an explosion. I'm going to get this stopper in really tight and see. Will I contain the gas? Oh yeah, it's fine. Nothing's happening. Whoa! Wow, could have fooled me. So you use both hands this time? I'm going to be honest, I don't think osmosis is that strong, but I can try to fight the pressure of gas. We'll see. Let's see. All right. Sorry, it was pushing my hand back, so my hand started to hurt, so that is my fault. Alrighty.